right. Well, good morning, Edward. Thank you very much for showing up today. You're going to give us a demo of Lingua Franca. Show us what you've got. Thank you.
Okay. Yeah. Let me share my screen. Try to make sure I share the right screen. Okay. So you should see a Lingua Franca program and a diagram that's generated from the program. And this is a federated Lingua Franca program, which means that the top level components, if we hide all the details, we see that there's 4 top level components. Each of these will be code generated into a separate program, and the code generator will synthesize the socket-based communication between these programs. And the fact that it's a federated program as opposed to generating a single program is because of this federated keyword right here, which in the diagram gets rendered as this cute little cloud to tell you that this is a federated program. And the idea here is that we have 2 sources of events that are both instances of this reactor class called sense that periodically generates events. And the 2 are instantiated with 2 different periods. One has a period of 500 milliseconds. The other one has a period of 1 second. And then we're taking the data from one of these outputs and processing it. And the interesting thing here is that the processing is actually taking quite a bit of time. It's being emulated. It's multiplying the value of its input by 2. So that's a rather trivial operation, but it's taking at least 35 milliseconds in physical time to do that. Okay, so that could model slow network connections or long computations, either way. But there's a physical time latency that's introduced in this processing. But the key thing is, so what do these sense reactors do? Well, they've got these timers that are triggering these reactions. So the reaction is just producing a counting sequence. So it updates a state variable that's a counter. So the first output from each of these at logical time 0, which is the start time of the program, should be 1, the value, just the value 1, the initial value of the state variable. And subsequent outputs will be incremented. And then the processor will take this 1 and multiply it by 2. The actuator here will just first examine the input from the processor. These reactions are invoked in the order they're declared. Actually, let me back up a second and explain that the times of the outputs here have both a physical time and a logical time. The timers are trying on a best effort basis to control the physical time at which the outputs are produced. Okay, so the output produced by this program will occur roughly twice per second. To the extent of that can be made precise on your platform, depends on your operating system, of course. But I'm running on Mac OS, so it's pretty good, but not microseconds of precision on Mac OS. But on RTOS it could be. Similarly, this guy, the second sensor, will be producing outputs roughly once per second. But the important thing is that these outputs also have a logical time, and the outputs are logically simultaneous because they have exactly the same timestamp at time 0, at least. At time 500 milliseconds, they're not. This one will produce an output, but this one will not. At time 1 second, they will both produce outputs, and so the outputs will be logically simultaneous again. The processing takes physical time, but not logical time. It's logically instantaneous. So the outputs from the processing will have the same timestamps as the inputs. So the timestamps here will be 0, 500 milliseconds, 1 second, 1500 milliseconds, 2 seconds, etc. When this component is presented with 2 logically simultaneous inputs at time 0 and time 1 second and time 2 second, for example, then it's guaranteed to invoke these reactions in the order they're declared. And consequently, the overall distributed program is deterministic in the same sense that a single-threaded imperative program running on a single machine is deterministic. The outputs that we see should be independent of the physical time that it takes to do this processing. So in particular, there's no race condition on when these inputs arrive at the actuator. They will always be processed in timestamp order. And when they have identical timestamps, this reaction will be invoked before this one, regardless of what is happening in physical time. So if we compile this program, what this compiler does is it'll actually generate 4 distinct C programs. We're using the C target here. It includes in those programs the coordination and communication infrastructure that's needed. And it generates as well a shell script that we can use for convenient testing to launch the programs. So I'll invoke that shell script and launch these 4 programs. So 4 programs start, and we start seeing output from them. We stop it and we can look at the output. We see that at logical time 0, the actuator reports that it received 2 and then it received 1. Why is that? Well, go back to the diagram. This guy at logical time 0 produced a value 1. This guy at logical time 0 produced a value 1. Okay. The processing, which is logically instantaneous, multiplied that 1 by 2, providing a 2 here at logical time 0, and the 2 was reported before the 1. Okay. 2 before 1, right there. At 500 milliseconds, there was no output from the bottom sensor, so we receive 2 multiplied by 2, which is 4. At time 1 second, again, we have logically simultaneous inputs, and they get reported again in the same order, irrespective of execution time, network delays, etc. Okay, so the distributed program is deterministic in the same sense as a single-threaded imperative program would be. And no matter how long things take to execute or communicate, we should see exactly the same sequence of outputs. Okay, but now let's suppose that this processing, this relatively large processing time of 35 milliseconds is a problem. Okay, because intrinsically, this introduces latency, which is the L in the Cal theorem. Okay, and as a consequence of that latency, there's a loss of availability in the actuator. In particular, the actuator cannot respond to the input from this sensor, this lower sensor, even though in physical time this input is available much earlier. Okay, but because of this determinism, the actuator cannot actually process this input until it has seen the outputs from this processing component that have logical times equal or less than whatever it's getting from this sensor. So there's a loss of availability. And we can see that loss of availability in Lingua Franca by setting a deadline. Okay. So what this does is this specifies that a deadline on the invocation of this reaction. In particular, what we're saying here is that we want this reaction to be invoked within 30 milliseconds of the production of the sense data. Okay, and while preserving determinism, that's actually not going to be possible, at least when there are simultaneous events because of the latency introduced by this processing. And so we should, in fact, end up missing this deadline. If we miss the deadline, instead of invoking the normal reaction, we invoke a deadline violation handler that is provided right here, which does almost the same thing. It reports the input, but it also prints a panic message saying we have missed the deadline. Okay, so let's compile this program again and verify that we do in fact miss the deadline. Okay, so it generates four programs again, and then generates a shell script that launches those four programs, and they start communicating. And sure enough, we actually do receive the same sequence of inputs. Okay, a 2 followed by a 1, but the 1 was late in physical time, and so it reports that in fact its deadline was violated. Okay, so from the Cal theorem perspective, what has happened here is that the latency introduced by this processing has caused a loss of availability at this actuator, and we're detecting that loss of availability by showing that a deadline is violated. Now, according to the Cal theorem, we should be able to regain that availability by sacrificing consistency. So if we sacrifice consistency, we should be able to gain availability. So how do we sacrifice consistency? Well, in Lingua Franca, the way you do that is by manipulating timestamps. So in particular, the construct in Lingua Franca that I can use is I can say, for example, to increment the timestamps on the connection between the processor and the actuator by 200 milliseconds.
Can you make that stochastic so it emulates the variability of, say, network delays?
Oh yeah, you can do that, although not with the after construct, but I can do that within this reaction. So, but actually, I mean, the way to emulate network delays is not by the timestamp manipulation. It's the amount of time that you sleep. So this is a distinction between physical time and logical time.
Right.
Right. So I can certainly make this a stochastic number to take a variable amount of physical time to do the processing. Okay. I can also make the logical time delays stochastic, but that will make the program non-deterministic.
Of course.
Okay. Whereas making the physical time stochastic should not make the program non-deterministic by itself.
That's the whole point. Yes.
That's the whole point.
That's the safety condition that you're looking for.
Yeah, exactly. So what we've done by manipulating this timestamp is the reason that this is a consistency property is think about it as, you know, this sensor is reporting the state of the world at time 0, for example, and this sensor is reporting the state of the world at time 0. But the actuator, when it reacts to those pieces of information, is going to be using stale information on the first input that is stale by 200 milliseconds. And what we're declaring here is that that's okay. We're okay with the actuator working with inconsistent data that's inconsistent by 200 milliseconds. Okay. So when it sees two simultaneous inputs, right, one of them is representing the state of the world 200 milliseconds ago, not the state of the world now. And so we declare that it's okay with us to have this inconsistency. And then we should be able to gain availability in exchange for that. And in fact, that's what happens in Lingua Franca. So let's look at what happens when we compile this program again. And then launch it. Okay. And now the behavior of the program is a little different because I have, in fact, manipulated logical timestamps. So the logic of the program has changed. So at time 0, it received only the second input. Why is that? Well, because at logical time 0, that's the only input available. There is no input on in1 at logical time 0 because of this 200 millisecond logical delay, right? So the first input that it will see on in1 will occur at logical time 200 milliseconds, which is reported right here. At logical time 200 milliseconds, these numbers are in nanoseconds, it received the value 2. Then at logical time 700 milliseconds, it received the value 4. Okay.
So what's the time resolution on your Mac OS system here? Is it microseconds or nanoseconds?
The time resolution that we use throughout the software is nanoseconds, but you don't get that precision from the Mac OS. I mean, if you access the timer using the appropriate API, it does report time in nanoseconds. But if you look at the Mac OS, it'll actually always have a trailing 3 zeros. So it's actually reporting only with microsecond precision, not nanosecond precision.
Thank you.
But so in this case, I could still end up with deadline violations, okay? But it's much more tolerant now of latency, okay, because of this timestamp manipulation. But if I change, for example, if the processing time is a full second instead of 35 milliseconds, I should once again start to see deadline violations. Okay, which is again the Cal theorem. Latency goes up, you lose either consistency or availability. I've expressed that I'm willing to lose a measured amount of inconsistency, 200 milliseconds worth, but there's too much latency here, and that's not enough to give me the 35 milliseconds of availability that I want. And so if I run this program now, I should see consistent deadline violations. Sure.
Yes. Excellent. Well, that's what's so nice about Lingua Franca. You can literally, give the system the logic that you want to be executed. And the notion of consistency needs to perhaps be expanded a little bit too, because when you receive an update, a value, that value in memory can, for example, be in the middle of, say, a two-phase commit transaction. And if you land right in the middle, the data structures can be inconsistent in the sense that they don't make sense with anything on either side of before or after until they're actually complete. And so the extension of the notion of consistency, the thing that Pat talks about a lot, I think is perhaps important here too. But you've got the mechanism in Lingua Franca to actually address that.
Yeah, I think one of the nice things about it is that it kind of nails down, makes very precise what the notion of consistency is, and
Yes.
And makes it quantifiable.
And you get to modify it with the way you do the reactors too. You can actually have, if I'm 1 millisecond late, do this, and if I'm 20 milliseconds late, do that. If I'm 300 milliseconds late, you do something different. And so I assume that you've got conditions like that the reactors can test against your assumptions about what you expect the system to do.
Exactly.
Excellent. All right, good. Well, thank you. What I'll do is I'll stop the recording on that so that we can put it up on YouTube so that Pat can see it as well.